Welcome and thanks everybody for joining. My name is Seth Lawler. I'm a computational science and informatics lead at Dewberry, and I'll be co-presenting with Murad and Jeff.
And this is Murad Bouhafs with Atkins, with Principal Technical Professional out of the Atlanta office.
And I'm Jeff Albee. I lead Stantec's newly formed Digital Solutions team. So despite our complicated title, our agenda today is pretty straightforward. I'm going to try to simply state the challenge given to us by our client, as well as our overall objectives to frame this solution, then dive into a high-level overview of the strategies we executed to deliver this project, with an emphasis on our team's fundamental strategies of agility and technology. And then Seth will take us home there and finalize with what we learned in findings. The challenge. Our challenge was to develop a rapid 2D modeling framework for executing probabilistic flood risk analysis for watersheds. And it is a challenge in that traditional flood analysis have largely been produced using deterministic methods, which don't really fully consider uncertainty. As a result, the flood hazard information has been open to criticism with respect to accuracy, as floods larger than those depicted on the firm maps typically do occur, sometimes do occur. The probabilistic method represents an exciting advance in the way we develop flood risk information, and that it works to address some of the traditional method criticism. The problem is that probabilistic flood risk assessments present many challenges as well to our engineers and scientists. Challenges like parameters for distributions and uncertainty, in addition to the need to run hundreds or even thousands of simulations, which, as we all know, can take a really long time and be pretty expensive.
So objectives were obviously meet the schedule. And so that's always the first and principal objective for any job. Not any different with this one. But we had some technical objectives that we outlined for ourselves, both in terms of how we wanted to approach this and how we thought we could be most successful at driving this. So cloud agnosticism, we wanted to build a framework, as Jeff said, and not a set of changes for a certain provider. And so we'll talk about it as we move forward, but we used a number of different solutions from different cloud providers and from different places to put together a framework that allowed us to execute, meet the schedule. And then modularity, we took a microservices approach. So a couple things were driving this. One, there wasn't a clear timeline, meaning there were technical folks, and that's the talk that we're giving today, that were putting together the scaffolding and the framework to be able to execute this. But we were working closely with engineers who are developing models at the same time. And so how that interaction between the engineers and the models that are developing and the tools and the framework that we're building to execute them kind of happened all concurrently. And so a modular approach is what we decided to use for this. And then focus on engineering. At the end of the day, what we're trying to do is run a bunch of models. Like Jeff said, thousands of models that we can perform probabilistic studies. And so we want to be in the background as much as possible, facilitating and helping the engineering processes go through. And then obviously seamless coordination is needed. We'll talk about that. And automation routines. Everything needs to be automated. And so that's what we sought out to do in this talk. I hope we'll show how we did that. So engineering agility. Agility or agile processes is something that we in computer science and development a lot, where we try to identify what we're going to do, put in timelines and procedures and sprints to get things done, and then evaluate how things are working. And we did that a lot in this process, once again, working with the engineers, where we had just-in-time trainings. We would be talking with the engineers, identifying what was needed, testing and developing, and then having meetings, many people on meetings of very different rounds to pull this together. And so I'm going to talk a little bit more about that. One way we did this was before or at the very beginning of the project, we set up a wiki page, because that's where we go to find things out. And that's where this resource was huge for us. For the technical folks, we went to look and understand what the engineering people were doing. For the engineers, they went to the wiki to find out what we were doing. And the Wikipedia page was really important on the engineering side in that it allowed all the modelers and the engineers to see the types of problems and decisions that they were facing and making so that we had a consistent approach. And so we set up a Wikipedia page, and that was used well. And then we put together some charts, and this next chart I'm going to show you on the slide coming up is from one of the just-in-time trainings. So this is a typical slide that we use to show the engineers how the process would work and identify processes. So I'm not going to go through this too carefully. I just want you to see that there's an engineering team and a tech team. And these two teams work side by side throughout this process. And so what you're seeing here is, which says essentially, we want to make sure we get this right at the beginning before we run 1,000 simulations. And as I mentioned, the modelers aren't used to doing things in the way automation engineers like ourselves do. So what we did was we put together a system, and the next slide will show it, which is identifying how everything should be named and organized in a normal file structure like you would find it in your computer, but ported to the cloud. And so we sat with the engineers and we identified a series of nomenclatures and taxonomy for all of the models and the tools that we used, and we put them through a test to identify A, if all the models were in compliance, and then B, if the models ran, the engineers could check them. So you can go ahead now, Ron, thank you. You can see here we used Amazon Web Services as our storing container for the blobs and for the engineering tools. And this is just a slide showing that everything was named the same. So we had uniformity. We also had scale tests. So the engineers would develop a model and then send it to us to make sure it would run in the cloud. And before we ran it 10,000 times, we would run a handful of runs to do a couple things: stress test the cloud environment that we're running it on, and allow the engineer to look at the model outputs after they came off of the cloud. And so you see on the bottom it says review results, actuarial points. This is not exactly what we're talking about in today's talk, but it's important, as Jeff mentioned, a probable. In some ways, the engineers were looking at their models in a different way, because what an engineer typically does is looks at the floodplain and see if that makes sense hydraulically, and if the overbank flow is where we think it should be. In this case, we're looking at houses, structures, where the damage might be. If the flood wave and the floodplains made sense in the places where structures were.
Leveraging technology. Technology has been, of course, a big factor in getting this analysis completed on time, on schedule, per the rules Jeff and Seth have explained. And we're going to cover a little bit more detail in the next few slides how this technology implementation that obviously made the cloud a big factor that was achieved. We used, in our implementation of the solution infrastructure, we used more than a dozen applications and tools. The high number is a direct result of the complexity of the systems, the different platforms used, Windows and Linux and other variations, the different cloud environments. We mentioned that we've been using AWS, which is Amazon's Web Services, and Microsoft's Azure, and simply the sheer size of the tasks to accomplish. We relied mostly on open source tools. The list shows a subset of those, like Python for scripting, RAS as the main hydraulic analysis application, Git as the repository version control for all the artifacts of the project, source code, documents, specs, etc., that you need to track when working in a large multi-user collaboration project like this one. Jupyter expands on Git to provide a web-based solution for creating highly complex documents. And Postgres, Azure Tables, and SQL Server are the backend enterprise databases that we've used to track the workflow progress as far as status of the thousands of simulations we've run. The tracking was mostly automatic since it was handled by the code we've developed as part of this solution. There are other tools we're going to sort of mention briefly, like PowerShell, scripting for Windows, Visual Studio for building applications and the custom Windows tools we built, Service Stack as the framework for building web services, and several others. On the Amazon services, as far as details go, the cloud infrastructure was mostly running on Amazon's AWS with connectivity to the user's Windows desktop and Microsoft Azure for database storage. The high-level hierarchy of the solution is what you see listed on this slide. SOM is a desktop tool that we've written to hide all the complexities of the workflow. Our main users, the engineers in this case, use SOM to manage the different flood analyses, runs from beginning to end. The simplicity boils down to an engineer initiating one simulation or thousands of simulations for that matter, click and run, and then letting the system handle the rest. The engineer can later on track the progress of the analysis, look at the results, and download the results when done, and complete the QA process. The process. The scheduler service takes care of scheduling a given simulation on a given VM and works in tandem with the load balancer service to create the needed VMs for the analysis or reusing existing VMs up to prescribed capacity. Remember, in simple terms, the user says 1,000 simulations. The scheduler says, what are my resources? Do I have 100 VMs? Do I need to create 200 VMs? It starts the process, and then the scheduler schedules the runs and put them in tasks and watches the overall progress. And the database web server just keeps track of everything. The database service is the the glue that get all the systems communicating with each other. You know, the SOM on the Windows desktop, the analysis running on Amazon, and then the database running on SQL Server. This slide just builds on upon the previous one. We see how the process is initiated once the input data has been updated to the cloud. What you see there is the blue icon, S3, which is the storage name for AWS. Through SOM, users notify the load balancer how she wants the simulation to be run. For managing the 1,000 simulation, we use the concept of batches. So you're running them in simultaneous batches, like same geographic region, same type of simulation, some statistical analysis, and then these are running. So 1,000 simulation could be broken in 2 or 3 batches, 200 each, 500 each. That's what it gets defined by the user, and then based on the resources available being the number of VMs in the cloud that you want to the user wants to create or has already pre-created. The scheduler will take care of starting the runs and based on those parameters and making sure that each resource is used to its full capacity. The runs, once are completed, are downloaded again to the S3 storage, and then they can be viewed by the user. This last slide, I'm not going to expand on it very much. This is just a detailed workflow of the scheduler. The highlight here is, which is a bit our objective, is in leveraging AWS and Azure, is obviously cost. It is very easy to say, I want to run 1,000 simulation in the next 15 minutes, but then there's always an optimal solution. Then instead of doing 15 minutes, you could do 20 minutes or 25 minutes, and the extra length in the analysis translates into cost savings. That's what scheduler workflow does. It just makes sure to optimize either a newly created instances of VMs or a pre-created pool, and tries to leverage it to its full capacity. Jeff?
Yep, thanks. And because we like a good challenge, they basically did most everything Murad just described in Microsoft Azure as well, which really did perform fantastically given the models we threw at it. We used the same tools in Azure that Murad had mentioned earlier, open source as much as possible, running RAS 5.32D, Git, Jupyter, PostGRE, and a variety of storage options, which I'll show on the next slide. But we mainly ran these services in Azure, and this is really more nomenclature, again, very similar to what Murad presented there. We used services like Batch, which was the service that really queries or queued up all the execution and the shell scripts on compute nodes. So Batch kind of orchestrated everything to run tasks, which were the commands that were executed. Those tasks and ran jobs, and those were in containers, and they were assigned to a specific computing pool. And each computing pool was sort of the resource pool for RAM, CPU, OSs, and all the scaling rules. And then each of those pools ran packages, executables, to deliver and do the jobs. Next slide. And as I described, here's a good diagram of the process itself. You can see the PFRA process. We built a storage account in Azure, which contained blob and SQL database. Orchestrated through Batch, it ran jobs on the left side for models. Tasks ran model run commands and RAS itself. And on the right side, the jobs, the task jobs ran the export or the mapping functions, water surface elevations and RAS mapper. Next one, Murad. And the technology really was successful, as Seth mentioned earlier, because we defined standard inputs and standard outputs. I think it was just critical that we took that process. It was very fundamental to our success in order to have the system work on either Azure or Amazon Web Services. Next slide. And real quickly, again, some more models to throw at you. Not to belabor it, but the agile approach that we took was really a great model up front. Running these scale tests to get engineers to verify and actuaries to actually look at the data and say, you know, that looks about right, before we scaled the model and spent a lot of time and money to run all the probabilistic events. The agile approach was critical. And then finally, when everything was all set, the technology was set up, the scale tests were run, we just let it rip. And it ran thousands of iterations, delivering that standard output that we defined earlier, which was ultimately just probability grids.
So for findings, we're going to revisit our goals and kind of ask if we were able to check them off or not. I'll say before I start that this was an incredibly exciting and fun project. And there were many, many people involved at many levels over several months. And we did thousands and thousands. We built models from scratch. We built frameworks from scratch and did thousands of simulations. And it was a lot of fun. And what you see here, we met the schedule. Yes, we met the schedule. And I think Jeff and Rod demonstrated that we were able to meet the cloud agnosticism goal we set as well. This chart here that you're looking at just gives you an idea of the numbers that we're talking about. So we did in the order of 10,000 over 10,000 models, and the average runtime was 1 hour, and that could be 3 minutes for a small fluvial model, and it could be 12 hours for a big fluvial model, or more than that. So you can imagine the spread on 10,000 model runs and how 1 hour. It's pretty interesting. 37 cents was the average model run cost, and total CPU hours would be 10,586, predominantly 4 core machines. And so during the scale test, one of the things that we tried to do was identify what the appropriate size machine was to run these on. If it was a big model and required more cores and was more efficient that way, then we threw more cores at it. We were able to identify that early on through the scale test. Okay, next slide, please.
I'll just add there, Seth, real quick on that last one, that those findings were just I think a 10 or 12 day period that we measured. We actually didn't measure over the whole project period. This was just one time when we really kept very good data on the number of models we were running and tried to compute some stats over that period to present these findings. The actual project took quite a bit longer than that.
Correct, yep.
So modularity and automation, I think we can definitely check those off. You can see here, as Murad mentioned, we use Git extensively for collaboration and version control, quality control to make sure everything was working and running well, and that we were all using the same tools in the same version. We had routines for auto scaling. You can see the Azure and the AWS autoscaling instance or repos there, metadata, comparison maps, databases, documents, monitoring, the website, the Git repo. We used it extensively to make sure that we had high quality services. And the focus on the engineering, I think, really came through in some surprising ways. So we got ahead of the game a little bit and were able to develop, using Jupyter Notebooks, QA/QC tools for the engineers. So one question is, okay, if let's say you modeled a river and we ran the model 5,000 times, how's an engineer answer the task to say, yes, all 5,000 of those model simulations worked out perfectly, there were no issues, there were no errors, they were great. So we helped build some tools using Jupyter to facilitate the quality assurance and quality control procedures for all of the modeling done. And so I said 10,000, and then Jeff said, notice that was just a small portion of what we did. So we executed over 50 simulations over the course of 20 days, more or less. And so just to give you an idea of what that might look like yesterday, that would be 115 years of continuous simulation on a desktop computer. There's no way this could be done outside of a cloud environment. So I think that's what we have. Jeff, Moran, I don't know if you want to add anything else, but I'll say thank you.
That's pretty much it. I guess this slide summarizes the benefits if nobody's convinced about the cloud. Running that many simulations on a single machine would have taken us 115 years. I don't know about you guys, but definitely I don't think I'll live 115 years to see that.
I'll reiterate, nice work, team. Way to go.
Right.
I think now we'll take questions and answers.
Thank you. All right, we are back. Sorry for the technical difficulties. It's always a little challenging on the first session back after lunch, I guess. So we're going to go through here and see what sort of questions we have that we can kind of build upon the presentation that was already given. The first question I see in here asks, how is this different than the insurance industry's probabilistic modeling that underpins that industry? So I will kick it over to you guys and let you have out that first question, gentlemen.
Sure, I'll take a stab at that. Typically, the insurance is run now using catastrophic models, and catastrophic models run scenarios nationwide on a number of different hazards, fire, wind, flood, etc. And so we just used typical flood models to do.
Okay, the next question I saw was from Jeff, and his question was there a reason for using RAS 5.0.3 instead of RAS 5.0.7?
I'll take that one. There's some background noise there. I think it's Bill.
Hey, Bill, can you mute?
Bill. There we go. Jeff, sorry for the typo. We did use 507, not 503. So after we saw your question, we popped it up and took a look. We used the right. We did use 507.
See, there we go.
The next question we have is from an Al, and he says, about knowing the size of the model of the watershed, it's hard to understand this table on the slide known as findings. I don't know if that's going to be too specific for you guys, if you know exactly what he's talking about in the presentation, but any insight you guys can provide to that?
Sure.
Seth, you take that one?
Sure, I can take that. So there is no uniform answer. We ran many models of different size and resolution over different durations, and show what that was showing was an average. We ran hundreds of models. You know, they could be as short as several minutes or many hours.
Okay. Next was a comparison made in the node efficiency of the individual model runs?
Seth, you want to try that one, or is Murad best for that?
I can take it. Yeah, so it's tricky, right? What we want to do is understand how to size the machine based on the model. And the model, there's no real way to do that in general without just running it. So using our scale test, we would run a couple of different instances. We would run the same model on a couple of different instances, and then perform a quick diagnostic to size or fit the instances that we would use for that model.
Okay. Next, we have a question from Kyle. He asks, why did you choose cloud computing over local supercomputing?
Murad, why don't you try that one?
Yeah, good question. A few reasons I can think of. Probably the main one is obviously accessibility. As it stands now, we do not have access to a supercomputer. Number two is the usability of the different tools we've used, as far as open source and their easy availability on the platforms we've used, which mostly are Windows and Linux. And then number three, probably the most important one, is a supercomputer will be very efficient for an application that is really designed as running multi-threading on 100, 200,000 multi-threads at the same time, which is unfortunately not the case of the RAS application we've been using. Our testing and optimization showed RAS to be mostly running on probably 2-4 threads at the most. Anything more than that, you don't gain any more speed. So that explains why using the cloud with several thousands of VMs was more efficient than using one supercomputer.
Yeah, I'd also add its cost. The cloud computer allowed us to take more of an OpEx model than a CapEx model, having to buy any sort of a supercomputer. We could just rent it as we went and use whatever compute we needed to get the job done.
All right, thank you. I've got another one here. Said, asking, are those Jupyter notebooks open source? And are there any examples on GitHub that someone could see?
Seth, you start with that one. You're the Jupyter man.
Sure. There are. Many of them are open source. They're on dewberry.github webpage. Right, they're pinned right at the top, so you can check them
out. Next question is from a Mark. He asks, how did you manage the upload, download challenges that are related to the file size?
I'll start with that one. It really wasn't that hard. I mean, the files were large, and we took that as a sort of a cost of doing business. Most of our data pipes were able to handle it, and it was just really an upload, download expense. It took a little time to transfer those files, but was well worth it in terms of efficiency once you started to run many iterations of those models.
And zip is your friend.
Zip is your friend.
All right, I have another question here from Raj. He's asking, most of the firms have existing infrastructure. It seems it can be solved using Docker or Kubernetes and create cluster computers. Do you see a problem with that?
No, that's what we used actually, right? In most cases, we used that technology to deliver these. Go ahead, Murad, sorry.
Yeah, exactly. I mean, in some instances, we used Docker, in some others we didn't, for the simple reason that Docker did not allow us to remotely bring it to the machine and control it, because we developed our custom load balancer that needed full control of the machines. That was somehow a limitation a little bit in Docker. So in those cases, we didn't use them, but in the other instances, we did use Docker as an alternative to creating VMs explicitly.
All right, next question. Related to the CAPEX business case example, did you perform a financial evaluation of the continued use costs?
I'd say that's going on now, probably in our firms individually, and we haven't really talked about the future of this platform or product. But no, we haven't together performed that continued use cost, though I think that is going on in our business overall. Elsewhere, if you mean the continued use of this platform in the cloud, that's something we're still evaluating. Seth, Murad, do you have any additional input there?
No, I mean, I would agree. I would say that one of the things that we found is we can spin up big machines to run bigger models faster and quicker, and so that can facilitate day-to-day work.
Yeah, well said.
And I think we have one more question here. It's from a Yao. Have you tried to utilize the cloud computing resources to calibrate the RAS model?
Go ahead, Seth, take that one.
I think we did that with the scale test. So as I mentioned, the scale test did a couple things. A, it helped us size the machine. It made sure that it ran. But it also, we would run 5 different versions of the model, and then the engineer would take it back and evaluate the results. So in that way, it helped perform the calibration, or at least provide the simulated runs for the engineer to perform the calibration.
All right, thank you, gentlemen, for your time to talk today, and I think we're going to go on to the next presentation.
Thanks, Jacob.
Yep, thank you.
Hello, and welcome to
The next
my
presentation
presentation.
is Are
My name is Mitch
Hydrograph
Blum.
methods still relevant? And the presenters of this are Mitchell Blum and Mark Forrest, both with HDR Engineering Incorporated.
Hello, and welcome to my presentation. My name is Mitch Blum. I'm with HDR Engineering. My co-author is Mark Forrest, also with HDR Engineering. And the title of my presentation is Are Unit Hydrographs Methods Still Relevant? I'm going to be talking a little bit about hydrology and then hydrologic transformation. This will be important to asking this question about unit hydrographs. I'm going to talk a little bit about 2D hydraulic modeling and how that's relevant to rainfall runoff simulations, and then some examples of rain on grid simulations, some case examples, and I'll come to some conclusions, but I do want to kind of leave this question open for discussion. So hydrology, what are the main components of hydrology? You've got precipitation as an input. It's either measured or it can be frequency-based, like the NOAA 14 data. And there's also a lot of temporal and spatial variability. So once the precipitation hits the ground or hits the trees or hits the buildings, you have a series of processes which can affect how much of that rainfall turns into runoff. You have interception, you have initial abstraction, you have infiltration, and then depression storage. Once these losses occur, then that rainfall then has to be transformed or transformation or converted into excess precipitation into a concentrated hydrograph at a given location. That's where we're going to focus this presentation, is on the transformation. So hydrologic transformation. The main practice that we all use is the unit hydrograph, and a lot of the computer programs that do transformation use this as well. A little bit of history about the unit hydrograph. First developed in 1932 by Sherman, and then there were a series of follow-ups and different methods that you've probably heard of. The Snyder unit hydrograph in 1938, the Clark unit hydrograph in 1945, and then in 1965 was the first iteration of the SCS type method. And then that was refined in 1986 by the NRCS. And TR55 is probably the most commonly used approach for hydrologic transformation. So these are some of the common transformations. There's Clark's, Snyder's, the SCS, which we've just looked at. There's a modified Clark, kinematic wave, and then user-specified unit hydrograph. I'm going to be talking about just a few of these to sort of point out some of the factors that we use in the computations that are what I would call lumped parameters or averaged parameters. So the Snyder unit hydrograph calculates peak using the term lag, which is the time for the most remote amount of water to get to the concentration point. It also uses a basin length and a basin length to centroid. So the L and the L sub C are sort of meant to represent shape factors. The shape of the watershed is very important when you look at its response to runoff. This shape factor is kind of an approximation or an averaging of the basin shape. So those are physical parameters that you have to estimate or look at. So let's look at the SCS unit hydrograph. The runoff is a function of precipitation, initial abstraction, and storage. Now that storage is computed using a curve number, and lag is also a component in this equation. Lag time, again, is an estimate. It's a physical parameter of the watershed, and so is curve number. Curve number is also a lumped parameter or an estimate of the watershed's physical parameters. It's capability to shed water, so to speak. So let's look at the Clark unit hydrograph. Your outflow is a function of a routing coefficient, the inflow or precip, and then the storage coefficient R. And you'll notice that the storage is highlighted in red, as were some of the other physical parameters. That storage coefficient is based on the watershed's shape or the watershed's response. But it is a lumped estimated parameter. It's kind of an averaging. So what are some of the limitations on hydrologic transformations? For the SCS unit hydrograph, the computation of lag, which is a direct input, is velocity based, and it's sort of an assumed parameter. If you think about the process of computing lag is a velocity based approach, and that means you have to assume some sort of flow in your system and some slope and channel configuration to get those components of lag. You're computing a time based on a flow, slope, and configuration, and getting a velocity. That's usually an estimate or a simplification. And you also have to assume a flow. It also assumes a single watershed shape. There is no shape factor for lag. And we know that basin shape can affect runoff characteristics or runoff performance. The Clark unit hydrograph is limited by that basin shape factor that we talked about. There are only a few choices for that basin shape factor. It doesn't take into account a watershed like the one on the right, which is kind of an odd shape. The Snyder unit hydrograph is limited as it's a simplification of that basin shape using the length and the length to centroid. So these are all methods that use some kind of surrogate for shape or watershed response. But again, there's a lot of assumptions, there's a lot of lumped parameters, there's a lot of averaging. Basin characteristics are simplified to average watershed conditions. The lag or the time of concentration calculation is simplified. And then lag can also vary for different magnitude of events. Let's say the 5-year, the 10-year, the 50-year, the 100-year. Typically, we only use a single lag for a watershed. This will vary for different events. Lumped parameters, such as curve number, those are simplifications of the geometry. And each watershed, as we know, is a very complex system and can react very differently. So we are sort of oversimplifying these methods. And these methods were created in time before computers. So it was necessary to simplify these. So let's talk about computer advances. Hydrodynamic modeling. Common methods of hydrologic transformation, these were all developed pre-computers. You saw that slide with the history in the 30s, 40s, and as far back as 86, when we didn't have very sophisticated systems. The computer hardware has gotten much, much better. We have terabytes of storage, we have very fast processors, we have multiple processors and cores. Some softwares are using graphical processors. The software has come a long way to take advantage of this computer hardware system. There's 2D and 3D hydrodynamic models now. We also have a lot more data available to us. Geospatial data availability. We have terrain, we have complex terrains, we have precipitation data in a gridded format, such as the PRISM data. We have a lot more data at our fingertips to do these kinds of analyses. So let's talk about hydrodynamic modeling. I'm going to focus specifically on HEC RAS 5.0.7 because that's what we used as our case example to compute transformations explicitly. It's a U.S. Army Corps of Engineers product. It's a 1D and 2D hydrodynamic model. It uses the diffusion wave and full momentum or St. Venant equations. You can have up to an 8-sided cell, regular or irregular cells, and it is a finite volume solution. Now, RAS uses a very unique computational routine where each grid cell has a sub-terrain surface or an internal terrain surface. So if you can see this example on the bottom, this would be your single grid cell. Now, RAS does computations, hydraulic computations along the face of the cell, but it also recognizes all the terrain within the cell, which means you can actually have a little bit larger cells and still have detailed movement of flow through the cell. Rain on grid. So why are these 2D models important? What are we doing with this new capability? We can actually use a rain on grid simulation in RAS 5.07. We take what we call the precipitation excess. Now that is the rainfall after all of the losses have been applied to it. So you do have to, at this point in time with 5.0.7, you have to develop that excess precipitation in another software such as HMS. You have to compute your losses through HMS or other. It's added as a 2D boundary condition, and then you literally put that excess on every grid cell in the model. The limitation is that there is only a single excess for each 2D area. You don't have variable precipitation. But the advantage is that you are explicitly calculating that transform. So you're taking that excess rainfall, you're hydraulically routing it through the system, and you are collecting it in the channels based on the topography and the roughness and moving it through the system explicitly. There's no simplification of parameters or assumption of flows. It's an explicit calculation. So considerations for the rain on grid. You have to be careful with your Manning's roughness. It's not a typical channel roughness or overrank roughness. It's for shallow overland flow. So you will have to typically increase your Manning's roughness. Collection channels should have higher resolution in the model itself and also lower N values or typical of channel N values. The grid resolution should be considered based on what your conditions you're trying to model, like the urban setting on the top right. Micro terrain features become much more significant, such as buildings or berms, So you have to capture those features in your modeling. Terrain accuracy could be a limiting factor. If you don't have that much accuracy in your terrain, the water will not be allowed to flow, collect and flow as it does in reality. One of the other considerations is that RAS does not have subsurface drainage at this point in time. So those are some of the current limitations. Those are some of the considerations, so to speak, for 2D modeling rain on grid. Some of the limitations of the current version of RAS is that, as I said before, it does not compute losses from rainfall. The input must be a time series rainfall excess. You can only apply one time series to a single 2D domain. There's no spatial variability in rainfall. Non-uniform contributions. So if you do have variable rainfall, you have to use multiple 2D areas and then connect them with connections, hydraulic connections, so to speak. And then subsurface drainage systems cannot be simulated. So I want to talk a little bit about one of the project examples that we're working on right now. This is the Pine Nut Creek in Nevada, and it's a letter of map revision. And this will be sort of a unique submittal because it will be using a rain on grid transformation. That is not a typical process for a low Mars submittal. It has been done, but I think it's been limited. So our watershed is about 55 square miles. There are 19 subbasins, as you can see on the top right. It's sagegrass to alpine or pinyon juniper. We use the NOAA 14 frequency rainfall. It's a 100-year, 24-hour event. Now, these events in our area tend to be very shorter and flashier, with peaking sort of towards the beginning of the event. So we used a 33% peaking position for the rainfall. So HMS was employed, and we used the SES curve number and computed losses based on, the overland characteristics of the landscape. Now, as you can see, this was able to be simplified without doing any kind of routing reaches because we don't need that transformation. We're doing that explicitly in the hydraulics model. So you just have to set up your basins with area and curve number and precipitation. And each of these basins pictured on the top right will have their own excess. And then that can then be fed into a rainfall runoff hydraulics model. It simplifies the construction of the HMS model. Now, we also use depth area reduction based on TP40 for each of these subbasins. So once we got our excess from the HMS model, we constructed a RAS model, and each subbasin was a 2D area, as you can see on the right. So the rainfall excess was applied directly for each subbasin. That was done through DSS. So the HMS model outputs a DSS file with a precipitation excess hydrograph. So we did use a little bit higher N values for shallow sheet flow. They range from 0.1 to 0.15 for the overland areas. And then the refined channels were typical N values because it's a deeper flow. You don't have that really shallow flow. And we refined the grid cells, as you can see. The red lines are break lines. We refined those cells and gave them typical N values. The model was run in full momentum with a variable time step. So hydrographs were output at each of these connections that you see here. These outputs, hydrographs, were then fed into a more detailed hydraulic model. So this model actually explicitly computed the transformation. This will be a submittal to FEMA for a letter of map revision. The runtime for that rain on grid simulation, there were a lot of cells. It's a large watershed. It's about 40 hours. But again, we have no guessing or simplifying or averaging of the transform parameters. There's no simplification or assumption of flow through the routing reaches. It's explicitly calculated. So there's no need to estimate a time of concentration. The model is doing that for you. Here's just kind of what it looks like with that rain on grid simulation into our subbasins. You can see that water is raining on the landscape and then moving through the system. And I'll go to a closer view, see how it concentrates in those channels. Now, this is the transform process. The model is doing this explicitly. And you can see further down as the water concentrates. So another case example, we did a project in Rincon, New Mexico. And as you can see, this is a comparison at the bottom left of an HMS version and a RAS 2D version for the concentration point at the bottom. They are very close. So this model is doing a very good job representing what you could have done in HMS, but you would have had to make all those assumptions. So let's talk about RAS version 5.1. There were limitations in 5.0.7, but HEC is working on the newest version, and this version will include loss functions. So you will be able to do those losses directly in the 2D model. There will be no need to use HMS or other. There's an SCS curve number method, the green and amped method, and constant and initial loss. These losses will be applied as spatially variable parameters. So you're not lumping them per se. You can use spatially variability. It will also have the capability to have spatially variable rainfall patterns. So gridded rainfall data and spatially variable landscape data, such as curve numbers, the model will compute losses and then route the rainfall excess through the hydraulic domain. So that is a huge advantage. You will not have to go outside of HEC RAS. So just some conclusions and some food for thought. Traditional unit hydrograph methods make assumptions based on flow and channel configuration. They're pre-computer simplified approaches. They are lumped parameters which simplify the system. HMS unit hydrographs for many basin types, they give reasonable answers. They give reasonable answers with less computational time. So HMS runs very fast. So if you're looking for a reasonable answer in a very quick time frame, you may want to still use HMS or other. They take less computer resources, you know, as far as storage or processor speeds or anything like that. 2D modeling, if you're doing explicit transformations, you know, there is no guessing or lumping of parameters. The model is doing the transformation explicitly. It's a hydraulic calculations. You know, we should be taking advantage of this current technology. You know, then we don't have to make these guesses or these simplifications of our watershed. You know, you will also be able to run sort of a Monte Carlo capability with this 2D hydraulic model. The downside is that there are longer run times and you need a lot of storage and computer horsepower. So just a recap of some of our conclusions with HEC RAS for 2D transformation. The current version, again, is single excess per subbasin. But coming out soon in 5.1, there will be spatial precipitation, which is a gridded data set. And you can also add point gauge data. It will also have infiltration, so you'll be able to do your losses and transforms within RAS. So that concludes my presentation. If you have any questions, I'd be more than happy to answer them.
All right, thank you guys for that wonderful presentation. I see we've had a a bunch of very good questions come in. Unfortunately, the two gentlemen who worked on this particular presentation were not available to be on the Zoom chat for the Q&A session. So we will make sure and get with ASFPM to get their questions to them to see if you could answer them. I being a planner by trade wouldn't be much help for you guys to try to answer these questions. So we're actually just gonna continue and move on to the next session. Our next session here is going to be listening to community feedback when performing hydrologic analysis, the Nisqually River case, with Anna Simões, and she is a senior hydrologist with STARR 2/Atkins. So that will be what our next session is. And if you were coming to hear the question answered from the last one, I am sorry for that, but the two gentlemen that did the presentation were unavailable today. So we will be moving to the next session here shortly.
Good afternoon, everyone. Thank you for attending this presentation. My name is Anna Simões, and together with Farron Affleck, I had a chance to work in this unique project where listening to community feedback led us to a slightly different path than what we typically take. This hydrologic analysis is part of a FEMA risk map project to revise flows and floodplain maps for the Nisqually River watershed. The analysis was completed about a year ago, but the risk map project is still ongoing. We actually had its flood risk review about a month ago. A quick run through what I'll be covering. First, I'll be talking about the Nisqually River watershed characteristics and flooding history. Then, what is a minimally regulated flood event and how to develop a minimally regulated peak discharge record. Next, I'll talk a bit on how we extended the record according to Bulletin 17C guidance. And finally, I'll be presenting results. A few facts about the Nisqually River. The Nisqually is one of the most important rivers in western Washington, draining about 700 square miles from Mount Rainier to Puget Sound. As you may be able to see in my tiny Washington state map, the watershed is located just south of the city of Seattle. As for most of western Washington, Nisqually floods typically happen between November and February. One important characteristic of Nisqually River flows is regulation. Since the early 1900s, the lower Nisqually has been affected to some extent by flow regulation. And for the past 70 plus years, the most significant source of regulation has been Alder Lake Reservoir. Alder Lake Reservoir is part of the Nisqually River project. The project is composed by two dams, La Grande Dam and Alder Dam. La Grande Dam was built in 1912, then upgraded in 1945. The one you see in the picture is the much larger Alder Dam, which was completed in 1945, and it created the 3,000-acre Alder Lake Reservoir. Besides power generation, the reservoir highest operational priority is maintaining water levels downstream. Its second priority is to keep recreational lake levels during summer. So flood control is not a priority, but whenever possible, Tacoma Power, the project operator, lower lake levels during fall and winter. So that some peak of flood attenuation may occur, but it's no guarantee. In February 1996, the lower Nisqually experienced its largest event with widespread flooding and a lot of damages. The gauge at the town of McKenna, which is seen in the picture, during the 1996 flood, recorded an estimated 50,000 CFS. As you can see in the graph, that flow is higher than both the 1% and the 0.2% effective flows. So the 100 and the 500-year flows. So since 1996, the communities in the area have been using that event, this major event, for floodplain management instead of the effective 1% flow. So during project scoping, STARR and FEMA received strong feedback from the community in relation to impacts of regulation. Stakeholders said that effective flows are impacted by regulation and that regulation provides an unrealistic sense of security, causing flood risk to be underestimated, as most extreme events are unlikely to be controlled. Because of that, the communities wanted a hydrologic analysis that would account for natural, unregulated conditions as close as possible, or simply assume that the reservoir was full during major events. So FEMA and STARR agreed with the community request for using an approach that would resemble unregulated conditions. But the project had all the typical project limitations: budget, time, data availability. Anyway, it had some key data available, which we tried to take advantage of. As you can see in the watershed map, there are 3 USGS streamflow gauges strategically placed along the Nisqually, all gauges having more than 70 years of record. The gauge near National in the upper Nisqually is unregulated. That's the gauge most to the right on the map. The other 2 are regulated. La Grande, the gauge in the middle, just downstream of the reservoir, and McKenna in the lower Nisqually, where widespread flooding occurred in 1996. The other important piece of data that we had were around 60 years of data that we have from Alder Lake daily elevations. So flood frequency analysis is usually the method of choice in FEMA studies. So we decided we would apply it to all or some of the available gauge data. But despite we had those 3 gauges with long, reliable records, still we wouldn't be able to perform a fully unregulated analysis or an analysis that would follow the request from the community. So we decided on pursuing the idea of looking for events where the peak was not heavily impacted by regulation. Perhaps there were enough of those events so that we could perform frequency analysis on that subset of events. The basic idea was to look for events where available reservoir storage was negligible, which would lead to very little peak flow attenuation. These flood events would be minimally impacted by regulation, reason why we decided to call them minimally regulated floods. So, knowing that the February 1996 and the November 2006 were major floods in western Washington, we started looking at the gauge records to compare these 2 events. What we found is that upstream of the reservoir, the unregulated gauge near National registered record peak flows of the same magnitude for these 2 events. On the other hand, the regulated gauges downstream told a very different story, having the 1996 event as their largest event ever. But while the November 2006 was not even the largest event of that water year, of the 2007 water year. So when we start to compare the two events, we found that there was a really good a good example of what would be a minimally regulated and a regulated event. The November 2006 event would correspond to the typical regulated flood event. Reservoir water surface elevations show that there was plenty of storage available to attenuate upstream flows, with the reservoir never becoming full. When comparing the hydrographs upstream and downstream of the reservoir, upstream in green, downstream in red, we can see the flattening of the peak with much lower discharges downstream. A very different picture emerges from the February 96 data. When you look at the reservoir water surfaces elevations, we can see that the reservoir was full at the time of the peak in February 96. So no significant attenuation between flows upstream and downstream of the reservoir would be expected. And when you compare the hydrographs, that's exactly what they show. Again, green is near national upstream of the reservoir, and red is downstream at McKenna, where the 50,000 CFS peak was observed. At this point, we started to call the February 96 flood a minimally regulated event. So how do we develop a minimally regulated record? Well, we knew that we needed to identify events like February 96, events where reservoir storage was negligible and peak flow attenuation minimum. But to be representative, this record would need to include events both large and small. And how could we do this? Well, to support the identification process, we could use the same data as we did before. Unregulated flows upstream, regulated flows downstream, and reservoir elevations. If enough of such events covering a wide range of flow magnitudes, not just the largest ones, could be identified, a series of minimally regulated peak discharges could be developed and analyzed. We actually established 3 rules to help us identify minimally regulated events, so that we would have some objectivity. The first one is that the annual peak event is the same at both national and La Grande, so upstream and downstream gauges, and happens within a couple days between the gauges. The second rule, that the annual peak discharge is significantly higher downstream than upstream, implying no or minimum peak attenuation. And the third, that outer reservoir average elevation was high, close to the maximum, at the day of the peak at La Grande, indicating there was little or no reservoir storage available. When comparing La Grande's record, regulated record, against national's unregulated record, we were able to identify 19 events out of a total of 73. For these events, peak flows at La Grande ranged in magnitude from 6,500 to 40,000 CFS, where 40,000 corresponded to the 1996 flood. Minimally regulated peak flows showed excellent correlation against the unregulated peak flows upstream of the reservoir, as you can see in the graph. The same analysis was repeated for the gauge at McKenna, this time we used the events that had already been selected from the LaGrande national comparison. But since McKenna had a few gaps in the record, we ended up with 18 instead of 19 events. Again, we found a widespread range in flows and very good correlation against the national gauge record. So at this point, we could have moved ahead and performed the standard gauge analysis on the 19 or 18 identified events. However, to reduce associated uncertainty and improve our estimates, we took the extra step of extending the minimally regulated record using the MOVE method as recommended by Bulletin 17C guidelines. To give you perspective, the frequency curve obtained with the 19 minimally regulated events had really high skew coefficient for the region, and the 1% estimated flow was out of range of what we were expecting. So we thought we really would. It would be really beneficial to apply record extension. Since the minimally regulated annual peak flows were very well correlated with the unregulated peaks upstream, we used those to perform the record extension. So the short record was the minimally regulated record, and the long record was the unregulated record from the gauge upstream near national. Record extension and frequency analysis were performed for both gauges, both LaGrande and McKenna, but the results presented here only refer to the gauge at McKenna. After record extension, 14 events were added to the observed 18 minimally regulated events at McKenna. We also added a historic event from December 1933, which had an estimated peak of 42,000 CFS. And until 1996 was the largest flood observed in the area. The resulting flood frequency curve showed excellent fit, as you can see on the screen. It also showed the December 1933 event well aligned with the 96 event. Finally, we compared our 1% estimated flows for the gauge at McKenna. We only have effective flows for that gauge. And we also compared against historic flows. Our Bulletin 17C frequency analysis using the minimally regulated events and the record extension produced a 1% flow of 52,000 CFS, much higher than the effective 32,000, and in line with the historic floods of 1933 and 1996. So to recap what was done, due to stakeholders' request, the hydrologic analysis to update Nisqually River effective flows need to exclude or minimize the impacts of flow regulation due to Alder Lake Reservoir. The analysis applied involved identifying minimally regulated events, which are annual events that were not much affected by reservoir storage. We developed a new record with these events, a subset of the original record at each regulated gauge. Given that the minimally regulated record was much shorter than the regulated record, we used record extension following Bulletin 17C to reduce associated uncertainty. Finally, our results showed excellent fit and to be consistent with historical floods. And before you go, I would like to mention that there will be 2 other Nisqually River related studies being presented at the conference tomorrow. The first one by Sumya Sagarika during session E1, starting at 1:30 p.m. And the second during session F2, starting at 3:30 p.m. by Farron Affleck, who co-authored the study I just presented. Thank you all very much for joining.
All right. Thank you for the wonderful presentation there, Anna. We appreciate you going through all that stuff. When I took a look at it, I found it very interesting that the curves there, the proposed curves and the historical information were well aligned. I don't know if there's anything additional. I will look to see if what questions we have had come in related to this, but if there's anything that you would like to add beyond what sort of information you presented there, we'd love to hear it. I'm looking to see.
There are a couple of things that I want to mention. Number one, I'll be at the Atkins booth, the virtual booth, today from 5 to 5:30, tomorrow same time, and also on Thursday from 1 to 1:30. There's one slide that was missing apparently from the presentation that there will be 2 other Nisqually River related presentations in the conference. One tomorrow, both are tomorrow. I cannot remember the exact sessions, but one is from Sumya Sagarika and the other one is by Farron Affleck, and Farron co-authored this study. So.
Well, that's great to hear, and we had a couple comments come in there. People saying that it was great forensic work that you were doing on that very complex situation. They appreciate it. But here we go. There is a question that just came in from Sonia saying, maybe I misunderstood this. Did the statistical analysis combine regulated and low regulated flows to extend the record?
No. What we did was we had one gauge that was unregulated, and we had 2 other gauges that were regulated. And we compared we tried to find these minimally regulated record events from, by the comparison between one of the regulated gauges and the unregulated one. So there is no there's no combination. So the first step was to find these events. Once we found the minimally regulated events and selected those out of the regulated record, then we performed the extension. And the extension basically is, the idea is that those minimally regulated events, they are very well correlated with the unregulated record. So you can perform this record extension following bulletin appendix 8 of bulletin 17C guidance. So that's what it is, in the gist. And if you want more details, we can certainly talk another time, or I can provide you, or either by email or or at the Atkins virtual booth. So I hope that helps.
All right, thank you very much. I think that looks to be the only question we had beyond the several comments about what a good presentation it was. So unless somebody else has something else to add to the question box, or if there's something else you'd like to close with, Anna, I think that will do it for today.
Yeah. Well, thank you very much for joining, and thank you, Jacob, for the introduction. Thank you. Thanks.
No problem. Yep. Thank you, and everybody have a good day.